Good afternoon. I'm Josh Goldman, co-founder of KoBold. Thank you so much, Jeff and David, and the whole MineralX team for this incredible event. There have been many great talks the last couple days. I'm very excited about this one because the speakers you're going to hear from are going to tell you about how we are going to discover more of these deposits of critical minerals. If you care about having enough metals to supply the global economy, then you should care a lot about how there is no unique solution to the problem of geophysical inversion. It's very important. What you're going to hear about from these speakers is how one of the most common types of analysis that's done with geophysical data is flawed, and how better methods are going to help enable the next wave of discoveries, seeing deposits that are deeper below the surface and harder to find. And you're going to hear about technical topics, very technical topics, presented in a way that all of you can understand. I will be judging your comprehension as the audience by the quality of your questions. The speakers are my colleagues, Beth Reid and Lauren Anderson, who are both data scientists at KoBold. They're going to be telling you about one of the many dozens of tech development programs that we have underway. Beth received her bachelor's degree in math and physics from Virginia Tech, her PhD in physics from Princeton, was a postdoc at the University of Barcelona and a Hubble Fellow at Lawrence Berkeley Lab. As an academic, she used 3D maps of galaxies to understand what the universe is made of and how it evolved. She then worked as a data scientist in the tech sector at Climate Corp and then as a software engineer at Google. Lauren received her bachelor's degree in physics and astronomy from UC Berkeley and PhD in astronomy from the University of Washington, then did postdocs at the Flatiron Institute and the Carnegie Observatories. As an academic astronomer, she worked on topics like the formation of galaxies in the early universe. She was motivated to work on climate change solutions and joined a solar power startup company as a data scientist. At KoBold, Beth and Lauren have two roles. They are explorers. Each of them is working on an exploration project that they co-lead with a geologist, using our technology and our scientific knowledge to try to make a discovery on that project. And they do R&D, developing new technologies to make us better explorers. It's also fitting that here at the Silicon Valley Minerals Forum, you're hearing from these brilliant scientists who have come from other sciences, physics and astronomy, and have become now exploration geoscientists, and who've come from other top tech companies to join KoBold, a mineral exploration startup. As you heard about in the last panel before lunch, this is the sort of brainpower that we need much more of in exploration, not just at KoBold, but across the whole industry, because that's how we're going to make the breakthroughs that we need to improve exploration success and find more materials. So with that, Beth and Lauren, over to you.
Hey, good afternoon. So one of the goals at KoBold is to reduce the number of drill holes we drill per discovery. And as we heard yesterday, right now we're currently in mineral exploration drilling hundreds of holes per discovery, whereas oil and gas, it's about 3 per discovery. So there's lots of room for improvement there. And so Beth and I will be presenting on geophysical techniques KoBold's working on to reach that goal. Beth will be presenting on a nickel exploration project, and I'll be presenting on a copper exploration project. So to start off, we're going to retell a parable that many people may have heard before of some blind folks meeting an elephant for the first time. So each blind person goes and touches the elephant in a different location and tries to come up with hypotheses for what the elephant is. So one guy goes up and touches the tail and finds a wiry tail and hypothesizes, ooh, this is a rope. And another one goes and touches the leg of the elephant and hypothesizes, oh, this is a tree trunk. And it's not till a sighted person comes along that informs them, you know, you were right in detail, but by only having a very limited view of this elephant, you sort of missed the bigger picture of the elephant as a whole. And so now Beth is going to share how that relates to mineral exploration.
Thank you, Lauren. So we are going to pull you along with this parable. But before we do that, so we're talking about how we're going to use geophysics and drilling data to make discoveries faster and with fewer holes. So What is a drill hole? Well, as far as I'm concerned, this machine that you see on the left, its job is to extract drill core. Closer, thanks. Which is Bobile is holding a piece of that in the figure there on the right. So you have a couple of centimeters in diameter, and then a kilometer more underground. So that data is extremely rich. You can measure chemistry, you can measure mineralogy, you can watch as you go through different strata. So fantastic information, very local. Going back to our analogy, drill holes are like those blind men's touches. Really detailed information. It's easy to miss the big picture. And unfortunately, we don't have this mythical person or technology that has true 3D underground sight and can just tell us, like, that's what you're looking for. So the next best thing that we do have is geophysics. And I want you to conceptualize that as a variety of different ways to have a blurry but a holistic view. And so in this picture, I've just taken our nice image of an elephant and I've blurred it out. So you can think of this as a prediction for how would this elephant look if you had a really bad camera that was out of focus. What I see is a bear. So maybe you don't know what kind of animal it is with this sort of resolution. We don't see the tail anymore. I don't see any tusks, but you do get big picture information. I know what color this thing is. I know roughly how big it is. So those are kind of the two extremes of the information that we're working with. All right, so to state the obvious, blurring an image is very easy. So if I start with my high resolution elephant and I blur it, I know exactly what I'll see through that blurry camera. All good? Okay. All right, so now we're gonna get back to geophysics. So the analogy holds. What you see on the left is an image of a very simple 3D model of the physical property of conductivity. All of the transparent area has conductivity 0, and you see a blob. That guy has some conductivity. So that's a simple model in 3D of conductivity. And from that model, we can easily predict what we would observe in a geophysics survey, in this case, an electromagnetic survey. And all we need to know are the laws of physics. Those are very well established for hundreds of years. So that part is easy. What is quite impossible is to go in the other direction. So as we talked about with our blurry elephant, we've lost a lot of information. I don't see where the tusks are. I don't see where the tail is. Similarly, we cannot solve these equations in reverse. Take our geophysics image and uniquely predict conductivity in 3 dimensions that gave rise to that observation. All right, I know you're all tired from lunch and you are going to put on your geophysicist hats. I'm going to give you 10 seconds. Take a look at these images. Note down which ones you think contain one or more elephants. I'm sure Kurt is going to send you a bottle of wine if you get this perfectly right. So make evidence. All right. Ready? Okay, these 3. Anybody nail it? Yeah? All right. Talk to Kurt. Okay, fantastic. So that is the hard job of a geophysicist. And there's no right answer. All right. All right, this is working. So the standard process in industry, so obviously all we have usually is geophysics data. We want to recover what is actually happening underground. That's the impossible inversion problem. And so a standard approach in industry is to disregard the impossibility of this and apply additional smoothing and regularization constraints in order to get an answer. And this is an image that represents that process. So number one, you get one answer through this process. Number two, it's geologically implausible. The constraints that we've added to the problem do not lend your solution to match geological expectations. So first thing we see here is that this AI elephant has the wrong number of trunks and tusks. And the real problem, so number one, it's wrong. That's a problem. I might hand this one result to my elephant hunting friend, and he's going to get really excited by those big tusks on the back. Maybe he'll drill a hole there, and he will find nothing. That's a problem. The other real problem is that there's no uncertainty associated with this. So sure, like there is some kind of pink blob, maybe it's an elephant. We don't have a sense of which parts of this result are well supported and robust in the data itself, and which parts are kind of hallucinations like we see in AI. So what is KoBold doing to address this problem? I would say there's two really important things I want to convey. Number one is, even though we're hunting for elephants, that's not all we model. Every time we're faced with a problem, we want to enumerate a lot of different possibilities for the things that can explain the data that we're seeing. And so in this case, I've enumerated our possibilities as distinct animals or distinct hypotheses. Once I've done that, I can generate millions of variations on these themes and explore in parallel. This is the kind of KoBold sweet sauce. We use the fact that the forward modeling part is easy. So we generate a lot of possibilities, and we want to figure out which ones actually fit the data, which ones might be the right answer. And so as we go through this process, we predict what we would see in our blurry camera from our lion at the top. We make the blurry image. We compare it with the observed data that's over there on the right, and we decide that doesn't fit very well. So we throw that possibility out. We can do the same thing with this rhino and with this picture of the elephant, and they kind of look like our geophysics data. And so those might be things that are left in our possibilities. And once we have this kind of complete set of possibilities, we use that whole set for our exploration decisions. We don't just focus on a single possibility. All right, so that was a nice bit of theory. Now what we're going to do is focus on two different stories of how we apply this technique. All right, so as Lauren said, I work on magmatic sulfide systems. These are ways to concentrate the group of nickel, copper, and platinum group elements. The source of these metals comes from the mantle, and you have magma that flows up from the mantle into the crust along this cartoon blue structure that I've labeled there, a magma conduit. And we need two more things to concentrate our metals into economic concentrations. First, we need to add sulfur to the system. Sulfur preferentially will leach out the metals, and they will attach to sulfur, and we'll have that distributed in our magma. The second thing that we need is fractional crystallization and aggregation through gravity to kind of bring all of those metals together. And if we get all of those ingredients, we can get a magmatic sulfide economic body that's shown in the red there. And I would say this picture is quite optimistic for two reasons. One is that many of these magma conduits don't actually have those necessary ingredients and don't host economic mineralization. And number two, the scale is deceptive. These conduit systems can extend for hundreds of meters or kilometers. And so it's really a needle in the haystack problem of identifying where in that system this material might coalesce. And for that problem, we use time domain EM geophysics. This is a method that is sensitive to the conductivity of a material. So conductivity is an inherent physical property of a material. It tells you how well can currents flow in this particular material. And what I'm showing all along this slide is a variety of materials and their conductivity. So all the way on the right, we spent a lot of time already in the last 2 days talking about copper. It's extremely conductive. And all the way on the left here, we have those conduit host rocks. So we expect our metals to be in association with these rocks, and they are basically invisible to our surveys. So we don't know currents are induced in those. But the materials that we're looking for, the magmatic sulfides, those are about 1 billion times more conductive than their host rocks. And so we have a really great differentiation of physical property that we can probe with time domain EM geophysics. So seems like a simple problem, right? Go do an EM survey and you're gonna find your riches. Unfortunately, nature makes this a little bit harder than that. So I've zoomed in to that conductivity diagram, and I've added a couple of other conductors that we often encounter in areas where we're exploring. So there are both graphite and pyrrhotite form in the sediments where these magma conduits have intruded, and those can often also be conductive. Quite conductive, and it's not easy to distinguish, or I would say impossible, to perfectly distinguish between these materials in our geophysics data. But there's a lot more information than we have than just that EM data by itself. And the property that we're going to use to kind of tackle this problem of distinguishing these two different types of materials. Again, the pink one is what we're after, and the green ones are not what we're looking for. And what we're going to use is the shape. So basically these things, these conductors, form from very different processes. When you're laying down a sedimentary bed, you often have these very thin and extensive regions of conductivity. That's these little bands in our gray box up there. And we already talked about the formation process of the magmatic sulfide. And the key feature that I want you to see here is that the magmatic sulfide is a little bit more blobby compared to these very thin pancakes that we might expect from sediments. All right, so just to remind you, we saw this earlier, what we're gonna observe is the thing on the right. What we wanna know is a model of 3D conductivity underground. Kurt, get another bottle of wine ready. We're gonna do this on a real problem, apply our methodology. And so I've put up here 2 different anomalies that we observed in different geophysics surveys. And they correspond to some conductivity anomaly underground. I've taken the surveys and put them on the same spatial scale. And what I'm showing you here is these type of surveys induce currents in the conductors that are underground, and we measure magnetic fields that are generated from the currents that are flowing in the conductors underground. And I'm just showing you one component of a 3-component measurement of those magnetic fields. Okay, so get ready to vote. Do you think, so one of these 2 is our target, a magmatic sulfide. It's quite difficult to figure out exactly what's what just from looking at this picture, as you might have guessed. The depth of the body, its conductivity, its size, its orientation, all affect what you're gonna see in this survey. Tough to distinguish by eye, but let's give it a guess. Who thinks the EM anomaly 1 has our prize?
Is there a difference between the fixed loop and the moving loop?
Great question. I thought there might be someone that knows what that is. So a fixed loop is, so the loop is what you, there we go, energize. So you drive current in a loop, and that induces the currents in the conductors. The fixed loop is basically, this one was probably almost a kilometer across, and we just laid it down on the ground and took a lot of measurements. These are both ground surveys. The one on the right is moving loop, so that means that you lay down the loop probably when there's snow on the ground, take a couple of measurements, and then you scoot the loop. So it has features that look more like airborne anomalies, if that makes sense. But other than that, there's at the same frequency. Any other questions? All right, anomaly 1. Let's see it. Okay, anomaly 2. All right, pretty mixed bag. Some of you are not willing to weigh in. All right, so let's go through this. So this is our bread and butter. So remember, we talked about having our different distinct animals, our different hypotheses for what this conductor can be. So for each one of these conductors, I've generated a whole set of possibilities, and every possibility that you're seeing in this animation are conductors that can explain EM anomaly 1. And we're just flashing through them. And so in the middle panel, you're looking at one particular 3D view of the subsurface and flashing through. We are modeling this conductor as an ellipsoid, and the colors are indicating the conductivity. So remember, graphite was the least conductive of our hypotheses, and magmatic sulfide on the right is the most conductive. And what I'm showing, remember, we're interested in the shape of the resulting conductor, so what I'm showing on the bottom is an edge-on view. So what is its longest extent along this x-axis, and on the y-axis is its shortest extent. All right, so let's, the next question we want to ask is, could this EM anomaly be explained by sedimentary graphite? So I showed this result to my geologist, and as you can see, it's often quite fat, tens of meters thick. And his understanding of the regional geology strongly disfavored this possibility. And in fact, if it were graphite, it could be economic to mine itself, because tens of meters of graphite is a lot. So with that result, we can kind of strongly disfavor this hypothesis for this particular EM anomaly. So let's go to our economic upside, the magmatic sulfide. We're looking at it on the right there. And remember, we want to use the shape as a discriminator. And so what I've done on this figure is I'm flipping through all my possibilities again on the right, and I'm summarizing their shape by taking the shortest axis, the y-axis on that plot in the bottom, dividing by the longest axis, and I'm plotting a histogram of all those possibilities. That histogram is shown in the green in the figure, and what I'm comparing it to is this black kind of choppy histogram. Those are a collection of known deposits and their shape. And so what I want you to read from this figure is that the green histogram is basically off the charts to the left of the shapes that we would expect to see from economic magmatic sulfide deposits. And so this is strong evidence that this particular EM anomaly is more pancakey shaped, like the image on the left, sedimentary origin, rather than the magmatic sulfide that we're looking for. So we've just walked through the sedimentary graphite and the magmatic sulfide possibilities. Nothing is ever 100% around here, but we've kind of strongly disfavored these two possibilities. And the one in the middle, sedimentary pyrrhotite, is a definite possibility. All right, let's do the same exercise for EM anomaly 2. All right, so same idea, different results this time, obviously different looking anomaly. So of note, these conductors all came out very shallow. Remember the feature that we observed was very compact. That corresponds to a shallow conductor. It's also much smaller. and it is steeply dipping, and that explains the positive to negative sign you saw in the diagram. So we can do the same analysis. Let's just skip right to our upside hypothesis. Now when we make this green histogram, you see that it is now overlapping with our distribution of known deposits. And so this permits the possibility that this particular target is a magmatic sulfide. So if these are the only two anomalies in KoBold's portfolio, what would we do? We would put our energy into exploring the target on the right. It has the distinct possibility to be magmatic sulfide, and we might deprioritize the target on the left. And indeed, turns out both of these targets have been drilled. The one on the right is in economic magmatic sulfide, and the one on the left is, as we predicted by process of elimination, sedimentary pyrrhotite. Cool. So how does this wrap back to our kind of big picture strategy of making discoveries with fewer drill holes? Let's come back to our animal analogy. What we're really after, the elephants, our goal in a big system with lots of possible elephants is to assign probabilities. So which one of these are most likely, given their shape, but all the other contextual information that we have, how they're oriented, where they are relative to their host rocks. This information can go into assessing which of these might be targets. And even if we can't figure out exactly what they are, if we can downweight our economic upside, then we can concentrate our energies on the ones with higher likelihoods. And that way we end up drilling fewer drill holes per discovery. I just want to briefly show you what a real survey looks like. We don't just have two anomalies. There's a whole host of information to disentangle. This is actually from the Cape Smith Belt. There's a poster outside on this same data set, but magnetics. And so, yeah, the big idea here is that we will kind of deconstruct the whole survey with this technique and focus our energies on the ones that are most likely, given their overall context and their results in this analysis, to be magmatic sulfides. And with that, I'm going to turn it over to Lauren.
Okay, so now we have found, right, a blur that we think is an elephant, and so we're going to take the energy and time to go touch it, right? We're going to initiate a drill campaign. And so we touch one side of the elephant, or what we think is an elephant, right, and we find a wiry tail, which is wonderful, right? This still supports our hypothesis that this is an elephant, but it doesn't fully test it. There are multiple animals that have wiry tails. So we're going to have to touch it again. And so the question is, where do we touch it next? And so one unique attribute of an elephant is its trunk, right? If we were able to touch the trunk of an elephant, then we could definitively say whether or not it was an elephant. And so if you were going to touch, or where would you touch next if you were going to try and touch the trunk of the elephant? At place 1, 2, or 3? 3, wonderful. Yeah, so you touch 3, right, because that's where we predict that the trunk would be. And so how did we make that prediction? Right, we took information about where the tail was, as well as this blurry image that we see, but we also had a good mental model of what an elephant looks like. Right, you could imagine if you didn't have a good mental model of an elephant, you might have to touch it multiple times. So an inefficient exploration program to finally get to the trunk. And so for this, right, it was a mixture of a good mental model of the elephant mixed with our previous touches and the blurry blob that informed where we should touch next to touch the trunk. And so in geophysics, it's a mixture of a good geophysical model mixed with previous drill holes and our geophysics to generate good drill targets. So Beth was using EM to explore for nickel bodies, And I'm going to be using gravity to explore for copper bodies. So for a gravity survey, what is being measured? So the gravitational force that we feel here on Earth is our mass times the gravitational acceleration, where the gravitational acceleration is proportional to the mass of the Earth divided by its radius squared. And what a gravity survey's goal is to measure variations in this acceleration on the surface of the Earth. So you may have heard 9.8 meters per second squared before. This is the average acceleration on the surface of the Earth. And so we're looking for deviations from that value. So as an example, if you change the acceleration of the Earth, you actually change your weight. And so if you were to stand on top of a gravity anomaly, which is a density anomaly, so let's say you're about 100 meters above a low density anomaly that has a density of about 2.5 grams per centimeter cubed. The background density of the Earth is 2.7, so this is about 10% less dense than your background. And it's about 50 meters on a side, just to give it some dimensions. The change in weight that you would feel from this anomaly is 0.00001%, right? It's a very small signal. It would be the equivalent of removing about 10 pieces of table salt from your mass. But this is actually 100 times larger than the detection thresholds of modern gravity instruments. So it's actually a significant signal, which is great. And so what we need for gravity to be an effective exploration tool is for there to be variations in our subsurface densities. Okay, the other thing to know is how these copper bodies form. So I'm going to be looking for copper in sedimentary systems. This is called sediment-hosted copper. And they form in, or there's sort of 5 main ingredients you need for these bodies to form. So first, you need the actual sedimentary layers that have been deposited on top of the basement. You need a source rock for the copper. So this is the original rocks that the copper came from, where it's very disseminated, like very low grade, very spread out. You need a briny fluid that's going to extract that copper from those source rocks. And that briny fluid is, salt mixed with water, and that salt usually comes from evaporated seawater. You need an aquifer that's going to allow for that briny copper-bearing fluid to move through your system. And then finally, you need some sort of trap that encourages the copper to fall out of that fluid in a very concentrated location. And that's what's going to create your high-grade copper ore body. And so the part that I'm going to focus on is the aquifer. And so we hypothesize that you need very thick aquifers to allow for a lot of that briny mineralizing fluid to be moving around, or copper-bearing fluid, to be moving around to hit one of these traps and generate a large high-grade deposit. So we want thick aquifers. Just a little closer? Okay. So we're going to be exploring on our Mingomba license on the Zambian Copper Belt. Y'all may have heard of Mingomba before because it's where we already have a high-grade copper deposit, which I've circled here in orange. The white outline is our license, and so the exploration question is, are there more high-grade copper ore bodies on the eastern part of our license? And so that's where we're going to be exploring. So we're going to take a slice through the subsurface to look at these sedimentary layers. So we're going to take a slice from A to A prime, and we're going to slice it like a layer cake and open up the cake so we can see the layers. So the top is the brown line. That's still the surface of the Earth, right? But now we're looking at the layers. So the y-axis here now is elevation. And each of the black lines I've drawn here are the separations between the sedimentary components that I'm going to be talking about. So on the top, we have overburden. This is weatherized rock. You can just think of it as disintegrated rock that sits on the top of the bedrock. Below that, we have the upper sediments that sit on top of this aquifer that we're interested in, that then sits on top of basement. And so the question is, right, we were curious, would a gravity survey be effective here? And for it to be an effective exploration tool, you need variations in your subsurface densities. So we went and measured the densities of the drills, or the holes that we'd already drilled in the area. And we found that the upper sediments and basement were higher density than the aquifer. So we have these variations in density in the subsurface that we need to explore. And one way to keep in mind that the aquifer is lower density is, right, this is the layer that was allowing for those briny copper-bearing fluids to move through them. And so you need porosity in order for that to happen. And so porous rocks will be less dense. So there's a historic gravity survey on our license. So we're back up out of the earth again, looking down on our claims. The white area, or the white line again, is the outline of our license, and the colored raster now is the historic gravity survey. And so gravity highs are represented by the dark blue areas, and so this is where you have denser material underneath you. And the gravity lows are the yellow areas, and so this is where you have lighter or less dense material below you. And so our hypothesis is that these gravity lows are where this aquifer is either thick or near surface. And so the exploration question is, what is the thickness of this aquifer? Right, because we want to find areas where the aquifer is thick. So a lot of this copper-bearing fluid could have moved through the system and possibly generated a high-grade copper ore body. So just to connect it to the analogy with the elephant, right, we wanted to test the elephant hypothesis. So we wanted to predict where the trunk was so that we could touch the elephant on its trunk. And so similarly for this exploration project, we want to test the hypothesis that there's a high-grade copper ore body in this basin. And so we want to predict the locations of the thicker aquifer to test and see if there's evidence of mineralization. So for the rest of this talk, I'm just going to focus in on this gray box of our license. And specifically for this example, so this is just a proof of concept. So I've created subsurfaces that we think represent the subsurface in the area to the best of our knowledge, and generated this gravity data so that I had some sort of truth to compare my model to see how well it's doing. So we have as our data, the gravity data that I'm showing here, where remember the yellow areas are gravity lows and the blue areas are gravity highs. And then we also have an exploration drill hole sitting right in the center of our survey. In addition to that, we have other drill holes that are sort of farther out beyond our survey, just to keep in mind. Okay, so let's slice the subsurface open again and see what these true surfaces look like that I used to generate this gravity data. So on the top, I'm showing depth as a function of easting, so as a function of location from A to A prime. And so at the surface, or at the top, you have a depth of 0, that's the Earth's surface. And then you have the depth to the top of the aquifer, that's about 300 to 400 meters below the surface. And then the depth to basement, that's between 400 to 600 meters below the surface. And on the bottom, I'm just plotting the thickness of the aquifer. So this is the difference between the top of the aquifer and the top of the basement that defines the thickness. And the black dashed line is the true thickness. And I'm pointed out here, right, this is the area that we're interested in. This is where the aquifer is thickest, where there might be a sense of mineralization. But the aquifer is actually a full 3D body. This doesn't just exist on this line. And so the way to think about it is that it's a bowl that sort of sits in the basement with a maximum depth of 300 meters that then thins out to 50 to 100 meters or so outside of that bowl. And so I'm representing that bowl as contour lines on top of the gravity data. So the contour lines here represent the thickness of the aquifer, where darker contours mean thicker. And so it's right at the center of this bullseye is where we're interested in targeting. That's the thickest area of the aquifer, and that's our target. Okay, so how do we infer the thickness of the aquifer? So for our data, right, we have our gravity data at the surface, as well as some drill holes. And so learning the subsurface from this data at the surface is this inversion problem that Beth described, where you have a fuzzy image and you want to infer the crisp image. but there's actually multiple animals that could have generated that same fuzzy image. And so similarly, there are multiple subsurfaces that could generate your data. So it's a challenging problem, but we persist. So one approach for doing the inversion is to separate up your subsurface into a bunch of 3D voxels or 3D pixels. So you have your underground subsurface, a bunch of 3D pixels, and you want to learn the physical property for each of those pixels. And by learning the physical properties from those pixels, you can start to say something about the subsurface structures. And so industry standard is to do a deterministic inversion. And so to remind you, this is like Beth's example of generating an elephant with a tusk, with a trunk on its forehead. And so you're learning the individual densities for each of those pixels, which I'm visualizing here. And so the densities range from about the density of the basement to the density of the aquifer. And the only real constraints on it is the densities need to vary smoothly throughout your space. And so you can see there's a lot of smoothness in this image, though there is some variation. But what we really want, right, is to understand the top of the aquifer and the top of the basement, right? That defines the thickness of our aquifer. But there's no real sense of surfaces in this model. But we can do it ad hoc afterwards by fitting surfaces of constant density consistent with the basement and the aquifer. And so when you fit those surfaces, you can generate then an aquifer thickness, which I show here. So we're taking a slice of the subsurface from A to A prime. And here I'm plotting the thickness of the aquifer along that slice as a function of easting. And so the black dashed line is the true aquifer thickness. Remember, it's about 300 meters. And the prediction from the deterministic inversion is about 4 kilometers. So it way overshoots the thickness, and it's definitely a very strong prediction. And so again, the aquifer exists throughout the whole survey. So what does the thickness look like everywhere? So here we're back on map view, so we're looking down on our survey, and I'm just plotting the thickness of the aquifer at each location. And so here, dark colors mean thick, and light colors mean light. And I've cut it at 1 kilometer. And so even 1 kilometer is too thick, but it gives you a sense of where the predictions are thick versus thin. And remember, we want to drill areas where there are thick aquifers to test our hypothesis of mineralization in this system. And so I would say that there's about 5 different regions where it suggests there's a thick aquifer that we would need to test. And so to put it as contours, like I did for the true thickness, it's hard to tell exactly what the contours are doing because the surfaces vary so strongly, but these are still the same areas of the thickest aquifer that we would want to drill. And so comparing this to the truth, right, we have one true drill target, but the deterministic inversion has actually suggested 5, right? And this speaks to that problem of too many drill holes per discovery, right? We'd have to drill 5 drill holes here when only one of them would actually be testing the thick aquifer. And so how can KoBold improve on this? So KoBold, we posit the same idea. We're gonna separate our subsurface into 3D voxels, 3D pixels, and learn the physical properties of each pixel. But we're gonna implicitly model the surfaces. Right, so we're in a sedimentary system, and so we'd like to put the constraints on our model that voxels that are in the same sedimentary package should have similar densities. And so that's exactly what this model is able to do. It's able to set up covariances between your pixels so that neighboring pixels in the same sedimentary package can have the same density. But in addition to that, we also allow for the surfaces to be probabilistic. So we're not just going to fit for the best surface. We're going to allow for the whole distribution of surfaces that are consistent with our data. And so you can imagine a suite of surfaces that are both consistent with the drill hole data. So they have to go through the region in the drill hole where you transition between the sediments. And that's kind of easier to imagine. But the harder one to maybe imagine is that it also has to be consistent with your gravity data. So the density, the subsurface densities have to also generate the gravity data that we see at the surface. And so by explicitly modeling these surfaces, we get a direct prediction for the aquifer thickness. And so here again, we're taking a slice through the subsurface from A to A prime, and I'm showing the prediction for the thickness as a function of location. And so the true thickness is the black dashed line again, and then the gold band is KoBold's prediction plus one sigma standard deviation. And so what you can see is that it definitely doesn't get it perfect. This is a really hard problem. But it does get the amplitude of the thickness as well as its general location, which are the two most important features. And so again, it doesn't just exist on that line, it's a full 3D structure. And so these are the predicted contours of the thickness of the aquifer using this model. And so again, darker contours mean thicker aquifer. And so it's predicted the same bowl shape that we saw in the true subsurfaces. And so comparing the two by using this improved model that explicitly models surfaces in this sedimentary system, we have one true drill target, and KoBold's model predicts one drill target as well. And so in addition to that, because we've modeled uncertainty, we can get a sense of which part of our prediction we're actually confident in. So with a deterministic inversion, you only get one solution, and so you have no sense of uncertainty. So you have no sense of where your model is more confident and less confident. But with our model, with the uncertainties, we can calculate this value called signal to noise. And that's basically your predicted value divided by your uncertainty in that value. And so larger numbers here mean that you're more confident. And so underneath the contours of the thickness, I've plotted the signal to noise. And so bluer regions are more confident. So the model is most confident where the aquifer is thickest. So in summary, by improving our model and explicitly modeling these surfaces in the sedimentary system in a probabilistic way, we've been able to test this thick aquifer hypothesis with fewer drill holes, which was our goal. The deterministic inversion suggests 5 drill holes, but we've only suggested 1. And so to conclude, KoBold is creating new geophysical methods to generate more informative drill targets that equates to fewer drill holes per discovery. Thank you.
Submit questions, please. Well, you can start with this one while you all are writing more questions. This question submitted for Beth. Is KoBold just rebranding existing solutions like Maxwell plate modeling with a tech narrative? If not, what exactly are you doing differently?
Oh my gosh. Did I plant this question? All right. Love it. So, I love plates, number one. And whoever wrote this question, all right, let's look at this guy. So, whoever wrote this question, you're exactly right. In this story, I've chosen really isolated anomalies. And the most important degeneracy in this problem is the conductivity times the thickness gives you a conductance of a Maxwell plate. And the reason that we see conductors that can be really thick and with small conductance is exactly because our solution is reproducing what Maxwell already knows. The problem with Maxwell is manifold. Number one, it is not an accurate solution to the physics. It was a solution that was written in the early 90s, aimed for the computers at the time, so there's really important approximations that it misses. Namely, if your primary field is varying over the plate, you get that wrong. It also doesn't solve the exact two-dimensional problem of how the currents flow, and this can give you markedly wrong predictions for your conductive body. So we solve the physics of plates exactly. But I think a lot more importantly, So why did Maxwell do that? We needed fast solutions to iterate. And so the way KoBold has dealt with the fact that EM is a nonlinear problem, and naively you need minutes to actually solve those 4 equations, these guys, is we've generated a surrogate model using AI so that we can model the simple system, but also much more complicated systems without having to solve the hard EM problem every time. I think there was also a poster about surrogate models, so go ask Jeff's students about that as well. So that's number 1. Number 2, which is really important, is like when you get a Maxwell plate and you're a geologist, you just think, like higher conductance is better. And we're trying to actually interpret that conductance in a quantitative way. And the way we've been doing that is making conductivity measurements in great detail on the core for targets that we do drill, and understanding like what we actually expect to see, relating that conductivity to what our models are producing. Because even measuring conductivity on the core is not telling you the macroscopic properties. And so we're building up a nice training set to understand that relationship in a quantitative way. And the benefits of doing that are that you're really able to understand the shape of your conductor better. Number 2, in these anomalies that I've chosen today, they're relatively isolated and well-constrained. That's not always the case. We often have multiple bodies contributing to a signal, and the technology that we have is not, we don't manually fit plates. We explore like the high dimensional space of possible conductors that can explain the signal. And we can also trace out, when you have lots of different plates that can explain the same solution, we can identify all of those rather than just one. I hope that helps. Feel free to identify yourself and follow up. Anything else?
Yeah, this is amazing stuff. In the oil industry 20 years ago, people came to me and says, I have seismic data. I'm going to do seismic inversion. And I do deterministic seismic inversion. And I take that velocity or density, and I make a net to gross map out of it. Net to gross means net versus gross, means how much pay facies you have, how much facies you have or rocks you have that contain oil. And so then people started drilling, and they found there was no oil, or they found there was a whole lot less oil. And the reason for that is, number 1, these deterministic inversions, they smooth out the subsurface. And for an oil company, a very smooth subsurface relative to another subsurface is a huge difference because you flow out the oil. The other thing that I saw a lot in the oil industry was we call these kind of plate models. We had other models like that we call drawdown curves, where people say we don't need the real physics. We can use approximate physics and derive to how an oil and gas reservoir would actually decrease in production, and how the pressure and the flow would decrease. That's great if you have a homogeneous reservoir, but it doesn't work when you have heterogeneity, right? And so what we're there trying to do here has been solved in the oil and gas industry. They only do stochastic inversions anymore, inverting the stratigraphy, the porosity, the permeability, building tens and tens of thousands of models that are all flow simulated. And everything else, like the drawdown curves and the plates and all of that, that's all long gone. So now you come back to the mining industry after a period of hiatus of 30 years, and I'm stunned that people do deterministic inversion and believe it and interpret it as if it is real. And I think if there's one inefficiency that you can solve today is what they do, right? You can solve this inefficiency today, and you can make not deterministic inversion, but invert for actual geological features that you know that exist, whether they are faults or layers of stratigraphy, just like the oil and gas industry did. And I think from my point of view, they're the only company who do that, except for our other partners, Ideon and Fleet, who are also moving into that direction. So kudos to you guys. That I think it's much needed overhaul of the industry, and getting rid of these deterministic inversions is going to increase your efficiency in everything, because as you see, uncertainty is what helps you make good decisions.
So his point was, what are you assuming to be the case, and how does that impact your thinking if it doesn't obey the laws of physics in terms of the way you're thinking about it?
I see where you're going. I think what he would be complaining about is that there is this floating ellipsoid right here. Totally with you there. That is not a geologic shape. But in fact, we are piecemeal building the complexity of what we're able to simulate, and we're learning from the data that we collect what the necessary complexities are to add.
So you say this method answers the question better than anything we've seen so far in terms of that question?
I guess so.
Thank you.
There's one more question. I don't know if we have time.
I had no idea how to answer it.
We'll
by
take
the way.
one more.
Can you say essentially that how we got from previous methods to the present is simply AI, and that had we had a better computer in the past, we could have accomplished the same result? Or is there another fundamental piece that I'm missing?
Yeah, great question. Well, we need ideas. And yeah, the computing helps a lot. And so how did we build this fast model to simulate complicated EM systems? We ran millions of these forward simulations and trained an AI model to understand that or emulate that physics. But I would say there's no reason for people to be stuck in the past of Maxwell, where people are kind of manually fitting models. Like that optimization is a solved problem. Like we can even if you're using Maxwell models, not doing it by hand is really easy, and it has been for a long time.
Okay,
We're out
thank
of
you.
time here. Please come up, and we've got a break now, so please come up and ask our speakers more questions. Thank you so much, Lauren.